Well, so today we're going to continue on our discussion of gravitational waves. We saw in the last lecture how gravitational waves have basically only two polarization states. Right? This is similar to electromagnetism, where you have a linearly polarized wave. It can be polarized in two directions, or you can have a circularly polarized wave. And so in this case, we also have that when we look at the wave equation, right? So the wave equation was box h mu nu is equal to something like minus 16 pi g times s mu nu. So this is the gravitational field, and this is the source, right? And if you look at an equation of this type, then you find that after imposing a number of conditions, namely after imposing the harmonic gauge condition and the local gauge invariance on the polarization tensor, right? Remember that the wave was written as some polarization vector, which we call E mu nu times e to the I k dot x plus complex conjugate, right? That the harmonic gauge condition implied, together with the gauge invariance, that you only had two polarization states, right? And those two polarization states had to do with E11 and E12. They were the only ones that were physical. And in fact, you can write it in terms of what would be the analog of circularly polarized electromagnetic waves in terms of E plus minus, which is equal to E11 minus plus I E12. And these E plus and minus correspond to a wave that is polarized with helicity either plus or minus 2, right? Suggesting that this wave has, in fact, a spin equal to 2. Right? And so it's quite remarkable that we only have 2 degrees of freedom. Right? Remember that the number of degrees of freedom in d dimensions is d times d plus 1, d plus 1 over 2, right? For the metric, because it is a symmetric quantity, and then from this we subtract the number of constraints that arise from the choice of harmonic gauge condition, and then we subtract the d from this, and so we get d times d minus 3 over 2, which gives, of course, in d equal 4, we have 2 degrees of freedom. Right? And in d equal 3, we have 0 degrees of freedom, right? So if we go down 1 dimension, then we are left with basically nothing, right? So the fact that you do have gravitational waves of this type is really specific to dimensions 4 or above, because as soon as you go down, then things don't work out anymore. So today we're going to look at right. So when you talk about gravity in 3 dimensions, it's got to be something that is fundamentally different than the gravity we usually think about, because you don't have this waves anymore, right? So today we're going to look a little bit more at what these waves look like, right? So nature of a plane wave, right? And so let's first discuss the case we're all familiar with, which is electromagnetism. So in the case of electromagnetism, what we do have are 2 polarization states, right? And those 2 polarization states correspond to light that is linearly polarized. So linearly polarized, for example, right, doesn't have to be that way, but linearly polarized is certainly the simplest case to discuss as opposed to circularly polarized. So in that case, we have that there are polarization vectors that point up for the first type of polarization, which we denote by A, right? And then you can have, for a wave that is traveling into the blackboard, right? So the wave is going this way, right? So this is the plane perpendicular to it, right? Electromagnetic waves are transverse. And, well, we also have a second possibility, right? And the second possibility is that instead of the wave being polarized along, say, the x direction, it will be polarized along the y direction for a wave that is, for which k is parallel to z, right? And so that corresponds to a polarization that looks like that, right? Looks like that. And so that would be case B. And now we can look at how these two things are related to each other, right? An exercise that we often do when we study electromagnetism. We see that one polarization can be rotated into the other by just a 90-degree rotation, right? So a 90-degree rotation will bring one into the other. So that means that if you do a 180-degree rotation of this guy, right, then you will bring it back into itself with a minus sign, right? So you essentially have the same polarization, but with the sign inverted. And when you do 360 degrees, right, you get back, if you want, the identity. So in other words, you return to the original state, right? And so that's what happens when you have a transversely polarized light. So in the case of gravity, we repeat the same story, except that now we recognize that because of the discussion we had last time, we're dealing with stresses. So if we have a gravitational wave, right, we're dealing with some sort of stresses, right? And we discussed the fact that actually the nature of the wave is such that you're describing a particle or an excitation that has spin 2, right? So you start out with a wave that has a polarization of this type, right? Again, in analogy with the electromagnetic case. And actually, I'm going to draw it. Sorry, it has to go outwards like this. And now we do a 45-degree rotation on this. So let's take an axis, which is located here, right? So we do a rotation by that angle by 45 degrees. Right? And so what we end up on this side is something that can be described in terms of these polarizations. In terms of these polarizations, because having an arrow that is pointing this way is in fact equivalent to having this situation. So we move the vectors back along the axis, and we can go from one to the other by this 45-degree rotation. So if this is A and this is B, we go from one to the other with 45 degrees. If we do a 90-degree rotation, then we get back to what we had originally, except with a minus sign, right? And when we do 90 degrees twice, right, then we have 180 degrees, and with 180 degrees, you go back to the identity, right? So as opposed to the electromagnetic case, where you only got back to the original polarization picture after 360 degrees, here you get back already after 180. And so that is, of course, again, a reflection of the fact that you're dealing with a wave that has a spin equal to 2, right? So after 360 degrees, right, you get two full rotations. Right? Now, if you want, we can complete this picture, right, by including the case that corresponds to a scalar wave. So third case, scalar wave, right? The case of a scalar wave, you can draw a similar picture, right? So a scalar wave would correspond, for example, to compressional waves or temperature waves, right? In this case, we have that we draw the vectors like this, right? Draw the vectors like this. And so that you have, as I said, some sort of compressional wave going into the blackboard. And of course, we do have a corresponding situation where we reverse all the vectors, which would be something that looks like this, right? And now the important point is that in this case, of course, you can rotate, right, situation A into situation B you can rotate into each other by doing any angle rotation you wish, right? Because this is a scalar wave, right? So there is no coming back after a fixed number of degrees. Any rotation will bring it back to what it was to start with. So this is the case of a scalar or spin zero, right? So in general, of course, we are familiar with the fact that at least in quantum mechanics, right, we have a rotation r by an angle phi, which is e to the I m phi, right? And that m is related to the spin by being a variable that is integer or perhaps half integer and runs between plus s and minus s. And of course, the scalar case corresponds to m is equal to 0, right? Where a rotation has no effect because it is just the identity. And then depending on whether you have spin 1 or spin 2, you come back to the original configuration either after 360 degrees or after 180. Now, we're not discussing here the case of fractional spin, right? Because in the case of fractional spin, of course, you have this oddity that for spin 1/2, you get back to the identity only after doing a rotation by 360 degrees twice. So here we're dealing just with bosons, if you want, scalar fields, things that are not fermions, so we don't encounter this kind of additional issues. So nevertheless, I think the result of this discussion is that the gravitational field, right, the h mu nu, is in fact, not unexpectedly, fundamentally different from anything that we have seen before, right? It is different from the electromagnetic field because it does have two polarization states, but those two polarization states are quite different from the linearly polarized states of an electromagnetic wave, right? They're still transverse, right? We're still transverse because we still have that this polarization vector E, right, is perpendicular to the direction of propagation. But nevertheless, it describes stresses. It describes stresses in the way I've indicated here, right? So it is quite different because of that. And the fact that the gravitational particle has spin 2 is intimately tied with that. And so this spin 2 or stresses sometimes are also referred to as transverse traceless waves. Transverse traceless waves, right? Or modes, right? And so it is a characteristic of gravitational radiation that they're transverse and traceless. Transverse, like in the case of electromagnetism, but also traceless, according to the discussion we had last time. So when you encounter in the literature somebody that talks about TT modes, right, then when they're talking about TT modes, they're referring precisely to these gravitational stresses, to the fact that they behave the way we've just described, and that they're transverse traceless. And this is a fundamental characteristic of gravitational radiation, that it behaves in this way and is different from the other two cases of spin 0 and spin 1, right? So that kind of completes the general discussion about the nature of the simplest gravitational wave, which is, of course, a plane wave, right? So a single monochromatic plane wave with a given k, right? And so that's fairly easy to sort out. And so the next step is what I've advertised as at the beginning of the lecture, which is written out here on top, which is the fundamental processes that lead to observation of gravitational wave. The first one is the process by which these are emitted, so the emission process and the absorption process, right? So that means that we are going to discuss next something that pictorially is going to be illustrated by, well, first of all, a source of some sort, right? The source, well, because gravitational waves are weak, right, you need a source that's really intense. Otherwise, you're not going to see anything. It's not going to be of great interest. So that means we have to have some sort of cosmic or stellar phenomenon by which a substantial amount of gravitational wave is emitted. So the source for that is, as we'll find out, something that has a significant quadrupole moment, right? Gravitational waves, in order to be generated, require the existence of a time-dependent quadrupole moment, as opposed to ordinary electromagnetic waves for which it's enough to have a dipole, right? As you learn in the electromagnetism class, you just need, in that case, an antenna, which is a charge that runs up and down a wire, right? That's going to give you a time-dependent dipole moment, and that is a good source for electromagnetic radiation, including the generation of radio waves. That's not going to work for gravitational waves, which need a time-dependent quadrupole moment because there's some sort of stresses and shear waves, right? So the natural, or one of the natural mechanisms to achieve something like that is to have a body, right? Now remember that gravitational effects are going to be strong whenever, as we discussed, I think, in one of the previous lectures, they're going to be strong whenever the mass is big and the size is small, right? So anything that is compact, right, and is moving perhaps also rapidly at the same time, and is heavy, is going to be a good source of gravitational waves. And so one situation to look at is the one where you have a binary object, and so ideally this binary object is two neutron stars, which are very compact, and so that would be a situation of, say, a binary pulsar. Right? So we are dealing with two neutron stars. Right? We talked a little bit about neutron stars in the quantum mechanics class last quarter, right? Remember that neutron star is stable because of Fermi degeneracy pressure, right? And it is very compact, right? So we're talking about radii that are just a few kilometers, 10 kilometers, something of that order, right? And so one is rotating around the other one, right? You can have, of course, pulsars which are isolated, like the Crab Nebula, I believe, as far as I know, it's a single pulsar, right? But so that's going to have some amount of gravitational radiation emitted as well, as long as its quadrupole moment is non-vanishing. But if you have a binary, that's a very good source, right? And so that, as we'll see, right, that will emit, that system as a whole will emit some gravitational radiation. And so what we need to be able to do is to write down some formula, right? And I think most of today's lecture is going to be quite descriptive. We're not going to go into any sort of details because we can spend quite a bit of time on just working out the basics of what the formulas look like for gravitational radiation emission, right? So it's going to be just a kind of a picture book overview, what we'll do today, right? So, but there's some details that will help us generate a large amount of gravitational radiation, such as the eccentricity of the orbit and so forth. And so if you have this good amount of gravitational radiation, then you need a detector, right? And because these are stress waves, you need something that gets stressed. It's stretched in some direction or another. And so the first thing that was actually proposed was a so-called bar detector, right? So a bar detector is a big chunk of material, typically some huge aluminum body, right? Cylindrical aluminum body. And then you have to, again in this case, kind of work out what the theory is for the absorption of gravitational radiation, again using the fact that gravitational radiation will couple to a quadrupole moment, and it is going to be some sort of stress wave, so you have to have the right setup, and then you can calculate how this gravitational radiation is going to get absorbed. And in doing that, of course, there's going to be two major steps. One is the determination of how each individual atom, each individual atomic absorber is going to absorb gravitational radiation within this thing, and then take into account the fact that instead of having one atom, you have n of them, where n is typically Avogadro's number, right? 10 to the 23 or so, right? So we have at the other end the process by which this radiation is going to get absorbed, and that will induce some deformation, right? Remember that gravitational waves are a reflection of a gravitational field, which does affect the metric, and therefore it affects the distance between objects. And so as a result, this bar will presumably resonate, and that change in the shape is going to be a signature for the detection of gravitational wave. Typically, it will have some linear size that we denote as r, and that linear size has to be in some relationship to the wavelength of the gravitational wave that comes in so that you can actually see something. It turns out that nowadays, in fact, gravitational detectors have quite a different shape than the one I indicated here. The original bar detectors were not very effective at detecting gravitational waves, in fact, detected nothing. And that was due to the fact that if the bar detector is the size it is, which is usually a few meters long, then there is way too many sources of noise around so that you can't really see the effects from a gravitational wave, which is intrinsically very weak, right? So you have a gravitational wave that is emitted by some binary system far away, in the case of the systems we'll be talking about, is maybe thousands of light years, right? So of course the intensity is going to get attenuated because of the distance. So by the time it reaches here, it's very weak. And so these kind of simplistic setups, which were originally discussed by Weber in 1961, right? So these are called Weber bars. They don't work very well because you need something bigger. So as a result, people have built now interferometers where the distance between the suspended masses is of the order of a mile, and the distance is monitored very closely by using lasers. So those have a much better chance of detecting something like this. Of course, ideally, you would like to have something that emits even more gravitational radiation than just a binary pulsar of some sort, because if you could have actually a black hole that swallows something that is nearby, or even two coalescing black holes, then of course by the time they get closer and closer and eventually collide, you would get a very intense burst of gravitational radiation, right? And so that would be something that would be perhaps more easily detectable, provided of course this inspiraling binary is located close to us, right? Because if it happens in some faraway galaxy, then there's less of a chance of seeing it. So the hope of the gravitational wave detector people is that maybe there's going to be some catastrophic effect nearby so that you can get a significant signal. So anyhow, today we're going to just focus on, well, the basic understanding of how these gravitational waves are emitted in the first place and what kind of formulas will be used in order to estimate the absorption cross sections, right? So, well, we're not going to have the time to do a lot of the derivations. In fact, I don't think we'll do any derivations. So we're going to write down a few formulas, and then we'll stare at them, and I'll give you plausibility arguments of why those formulas actually make sense and are useful, and we'll take it from there. So our discussion will be necessarily superficial. I mean, it's a big subject, so you can spend, weeks discussing the things we're doing today, and perhaps at some point we're not all of us are maybe interested in the most intimate details on how you calculate these things, and but you can find out more about it. I mean, the choice that we have made in this class is, of course, to kind of focus on the basic issues, right? So I think by the time we start talking about emission and detection of gravitational waves, we're getting into technical issues, right? So then we can perhaps just give the general idea and move on. So right. So the first aspect, and the other thing I wanted to mention is that, of course, a lot of it, when you look at it closely, a lot of the stuff that we're going to discuss yesterday is very similar to what you do in electrodynamics, right? Because in fact, in electrodynamics, you go to the same exercise. You will recognize that some of the formulas are different, but there's some similarities between them. Because in electrodynamics, again, we look at, well, you're going to see the correspondence very clearly in a little bit, but we also look at the emission of the emission of electromagnetic wave, and we usually do the far field approximation. That is, we look at how the wave behaves when we're at significant different distance away from the where the wave is emitted. And the second approximation which we're going to do also, which we do, of course, in electromagnetism and also in quantum mechanics when we discuss the interaction between radiation and matter, and which makes life so much simpler, is in electrodynamics the so-called dipole approximation. Right? We do this dipole approximation because that simplifies a lot of the calculations and matrix elements immensely, right? And so we're going to do the same thing here, because that will really make the formulas eventually become manageable. Of course, the only problem is that we're not going to do the dipole approximation, because dipoles are kind of irrelevant in the case of gravity. So we're going to go to the next end pole, which is the quadrupole. Right? So by doing this quadrupole approximation, though, nevertheless, you get formulas which are manageable. And of course, the steps that you do in order to derive these kind of approximations are the same as in electromagnetism. Right? The formulas will look different, but the steps are the same. So as a result, I think you will see some of the correspondences between the two theories. So the first thing we need to discuss is the energy and momentum and momentum of a gravitational wave, right? Because that is what will help us actually detect this wave in the first place, right? And so the point is that there is a T mu nu of x. Now, we have to remember that there is no such thing as an energy momentum tensor for a gravitational field in the context of the general relativity, right? Because, well, the nature of the gravitational wave is hidden in the Ricci tensor, the Riemann tensor, if you want. But nevertheless, we can split up the field equations in the vacuum, right, which is the Ricci tensor vanishing. We can split that up in a linear part and a nonlinear part. And the nonlinear part is then used as a source term, right, as we discussed, I think, a couple of lectures ago. And the source term is then the T mu nu of the gravitational field. So this is the energy momentum tensor for the gravitational field, right? And we have to put this in quotes because we're referring here to basically Minkowski space, right? We're referring to not a genuine tensor under general coordinate transformations, but just an object has two indices and behaves like a Lorentz tensor of some sort, right? So we had this discussion before, and so this is coming from the quadratic part of the Ricci tensor, right? The quadratic part, which is denoted by R2. And so that allowed us to write, remember, box h mu nu is equal to something times g, right, 16 pi g. And there was a minus sign in front, times the source part, right? And that source part is coming from the R2, right? And so that's this T mu nu here that we're discussing, right? So this is from the R2. Right? And so this was defined as 1 over 8 pi g, right? Because as we write down the field equation for the h mu nu, we have a 8 pi g in front, so we have to undo that by dividing this part by 1 over 8 pi g. And so this is the R2 part, right? The part that is of order h squared. Right? Remember, we're always doing this weak field approximation, so we write g mu nu as eta mu nu plus h mu nu, where this part is small, right? And that eta mu nu is just a flat metric, right? So Minkowski space-time. So minus a half, right? Remember that the source for the gravitational field is going to be this combination of Ricci and 1/2 eta mu nu times eta lambda sigma times r lambda sigma quadratic part cross parentheses, right? Whatever that is, that object, and I think we did not write it out explicitly, but nevertheless, all of this is of order h cubed. all of the remaining parts are order h cubed. So it's itself over the h squared plus higher order terms that we ignore. So now we write, as in the last lecture, right? We write h mu nu of x as a plane wave, right? So we write this as e mu nu times e to the I k dot x plus complex conjugate, right? So we write it as a plane wave. Single plane wave, monochromatic plane wave with a single frequency, and the H field has to be real, so that means we take that complex exponential and we add to it its complex conjugate, right? And so to make things tractable, we now consider a wave that is propagating along the z direction, as we did in the last lecture. So we take k. So we take k parallel to the z-axis, right? And from this, we can work out what the t mu nu is. So basically, we plug this in here, right? And there, right? And we'll look up what the quadratic part of the Ricci tensor is, insert it, right? And we get an expression for 2 mu nu, which is well, the only vectors that are left over, right, for a plane wave are the polarization vector, which is a 2-index object, and the k. So in this case, t mu nu is equal to k mu k nu over 8 pi g. Right, that factor remains, times the amplitude of the wave, right? We expect that the energy and momentum associated with the wave is proportional to its amplitude, like it is normally just for electromagnetic wave or harmonic oscillator, right? And so here we have E11 squared, open parenthesis, plus E12 squared, close parenthesis, right? And so question is, what is this average? Okay, why didn't he just write t mu nu? Well, the reason, of course, is the same reason that we, again, do it in electromagnetism and we do it in quantum mechanics, is that we have a plane wave, and normally we would have phases that survive, but we average over one cycle, right? We average over one cycle, we average over one wavelength, and when we do that, we just get this simple expression, right? So this is averaged over a few waves, lambdas, and over a few wavelengths or a small region of space-time, right? Average over t, and x, right? Average over some small region in t and x, which is the size of a wavelength or the size in time of a frequency associated with the wave. And not surprisingly, of course, what we do get is that the amplitude is proportional to the two amplitudes of the waves, which are gauge invariant, right? Remember that those were the only degrees of freedom left for a transverse traceless wave, was those two components. So we can rewrite this in terms of, so k mu k nu over 16 pi g. We can write it in terms of the E plus and E minus modes, and so we can write this as E plus squared plus E minus squared, right? And so it's the same thing, right? Factor of 1/2, because remember that E plus minus was equal to E11 minus plus I E12. Right, so we can write it either way, and so that's the expression for the t mu nu for a single electromagnetic wave. And in particular, this amplitude is now gauge invariant, because remember that that's gauge invariant. It is gauge invariant because only the E plus and E minuses are gauge invariant. Everything else you could adjust that to be 0. So, all right, so that's the energy of the wave in terms of the amplitudes, and we're not, of course, surprised by the fact that it is proportional to the amplitude of the wave squared. So now we come to the issue of generation of gravitational waves, So what we do is similar to what we do in the case of electromagnetism. So you have some source, right, which is located within a finite region, right? And typically this source size, let's take it to be R, some capital R, right? And that will emit some gravitational radiation, which will come out and will later be observed at some point X, right? And the point here that this X is very large, right? The magnitude, the distance at which you're looking at is very large compared to the size of the source. Right, now you do remember that the gravitational field h mu nu and x of t, because of the nature of the wave equation, can be written in terms of retarded potential, right? So the expression was that this is equal to 4g, right, times the integral over the source, so some integral in d3x prime, right, of the source term, which is this s mu nu of x prime, and t at minus x prime, right? So it's the retarded potential divided by simply x minus x prime, right? And this is very much like the expression in electromagnetism, right? You have the retarded potential. Right, and so now you would like to be able to pull some of this stuff out of the integral, right? And so the procedure, and by the way, let me remind you that S mu nu is the same as T mu nu for arbitrary sources minus 1/2 eta mu nu times T lambda lambda, right? That's how it's defined. So the S is basically the energy momentum tensor, except you subtract out one piece that is proportional to the trace. So now, in general, these sources have some definite frequency, right? Like in electromagnetism, there is a charge that is moving up a wire in the antenna, and that usually has some frequency, which is omega. And so it is useful at this point to write things in terms of Fourier amplitudes. So we're going to do the same thing here. We're going to Fourier decompose, right, T mu nu of x and t. We're going to write it as a frequency integral. So we're going to write it as an integral over frequency from 0 to omega in d omega of T mu nu of x and then omega, right, times e to the minus I omega t. And plus complex conjugate in order to make this whole expression real. So that is point number 1, right? Fourier transform. Fourier transform in the time. And the second point is to look at the far field. Right? So far field means that we expand x minus x prime. Right? That's just the square root of x minus x prime squared. And so this is going to be to leading order r, right? Right? So this point x is far away, right? So the magnitude of x is equal to r. So r is big, and so we can write this as x minus x dotted into x prime divided by r, right? So plus dot dot dot, which we draw. Okay, again, as in electromagnetism. And so if we do that, we stick that in here, right? In the x minus x prime, and again we expand because we have that object appearing in the denominator, and the leading term, of course, is just r, right? Which means that the leading term, of course, does not depend on x prime, so as a result, it can be pulled out of the integral. Right? So let's do that. Let's do that. Pull that out of the integral, and so we have that h mu nu of x and t right, and so is equal to 4g times e to the I times e to the I omega of r minus t, right? Remember that the speed of light, of course, is 1, so that's why we have just that combination. And then divided, as I said, by the r, which is what's left over of the x minus x prime to leading order when we look at large distances. And then some piece, which is left over, which depends on x prime, right? And so this integral, of course, is going to be over some region, right, which is that region that we indicated as this region here, right? And which is, of course, the region where the s is non-zero, right? So s mu nu is different from 0 here, right? So that's where the integral over x prime extends. And so what's left over is, of course, s mu nu of x prime, and then omega, right, times e to the minus I omega times x dotted into x prime divided by r. Right, and so this part here, we're just going to call it k. Right, k is equal to omega times x divided by r. Right, and so this is basically a unit vector, so we can note that by x with a hat if you want. Now the other thing is that we want to give this whole expression a name, right? So as a result, so we're going to have k is equal to x hat times omega, and of course k naught also is equal to omega, right? So you can make a 4-vector out of that. But the other thing is, as I said, we want to give that integral a name, and so the integral of 4g divided by r. By the way, this of course is a spherical wave, and you recognize that the e to the I omega r divided by r as an outgoing spherical wave, right? So the part that with the 1 over r times this other integral, we're going to give that a name. So 4g over r times, we are going to insert for it the expression of t mu, the s mu nu in terms of the t, right? So t mu nu of x comma omega, and we're going to look at the Fourier transform of that, right? And why the Fourier transform? Well, because this is essentially a Fourier transform, because this factor is e to the minus k dot x prime, right? K dot x prime, right? So we essentially have the Fourier transform of the s mu nu. So we might as well write it explicitly as a Fourier transform of the s mu nu, or given the fact that the s mu nu is related to the t by this relationship, we can just write it as a Fourier transform of t mu nu. So t mu nu of k, right? So you have the k, right? Minus 1/2 eta mu nu times, again, the trace, right? So it's the t lambda lambda of k and omega, and then square parenthesis. So all of this thing, we're going to call it what? Well, it's obvious what we want to call it, because this is an h mu nu here. It's the gravitational field. So, and we have a plane wave in front, which is e to the I omega times r. It's actually a retarded plane wave. And so it is very natural to write this as just e mu nu of k and omega. So we're going to define all of that like this, right? So basically we are writing this outgoing wave as some sort of just a plane wave, right? Or a spherical wave in this case, with a polarization vector that is clearly identified with all that stuff that appears in the integral, where the integral is just a simple Fourier transform. So if you look at it, actually all of this is quite simple, right? The only thing that makes it look more complicated is the fact that we always have to drag along this minus 1/2, right? Because it's in there and we can just get rid of it. And the fact that we have, of course, more indices, right? That this is not some sort of a scalar wave, but it is a tensor wave, and so we always have to have these two indices here, and the polarization vector is going to have more indices as well. But other than that, it is very similar to electromagnetism, right? So the next step in the case of electromagnetism is to look at the power that is radiated, right? So we're not interested in the wave itself, but we want to know what amount of energy is radiated per unit time. power radiated, say in watts, right? So in some sensible units. And so now there's two ways to describe this power. So it could be power as a function of the angle, right? In what direction is most of the power emitted from this kind of antenna type of setup, which is maybe an orbiting binary, right? And so it's the angular dependence of the power that is of interest. But of course, what is also of great interest and maybe a little bit simpler to deal with is the total power. How many watts totally is this thing going to emit, right? Which means you're going to, at some point, integrate over all the angles, right? Specifically the solid angle that is involved in this problem, right? So the first step in that is to compute the power radiated in a given solid angle, right? And so that is going to be related, right, by the formulas that we had a moment ago. Why is it related? Because we, first of all, have an expression explicitly for the field, h mu nu, and we also had an expression for the energy that this h mu nu contained, which remember was quadratic, right, which we wrote a moment ago on that blackboard, right? So this, putting in all the factors, is r squared times xi unit vector times ti naught, right? We want to look at the flux out of this region, right? And so that will involve the ti naught component. Again, it's an average over one cycle of the radiation, and it's this object here, which is like the energy and the momentum associated with the gravitational radiation flowing out of that region has to be dotted into something so that you get a quantity which is scalar, so it appears in this combination, right? And as I said, I'm just going to write some of the formulas and not go into too much detail. So Ti naught is, so this is an energy flux vector, right, which is analogous to the Poynting vector of electromagnetism, right? And so now there's a few steps in between to reduce this to a manageable form using what we wrote before, in particular this formula here. And so to relate that to the T mu nu, right? And so one can rewrite this as dP by omega. Actually, I need a little bit of space, so let me write this over on this side. So the end result so far, right, because we're going to go beyond that in a little bit, is that the power radiated in a solid angle, dP by d omega, can be written in terms of the T mu nu of the source, and specifically the Fourier components, which I described in a moment, come in when you do this. So it's the d times the omega squared divided by pi. The g, of course, is always there. And times, so Tij star of k and omega times Tlm of k and omega. Right? So remember, it's proportional to the amplitude square of the wave, so it's proportional to the energy momentum squared, right? We have gotten rid of the S, so we write things in terms of the T only, the Fourier components of the Fourier transform of the energy momentum tensor, as we defined it a moment ago. And but there's two indices on this side, two indices on that side as well, and so this is then multiply times some matrix, which is the matrix lambda ij comma Lm, which depends on k. In fact, it only depends on the direction of k and not its magnitude, right? So again, there's some similarities with electromagnetism, but some significant differences. Of course, the source for the electromagnetic radiation is this T mu nu piece, but also this lambda is a remnant of the fact that we're dealing with these shear waves. So lambda is a rather complicated sort of projection operator. So lambda ij comma Lm, right? We don't want to use the index k because that's already reserved for the wave vector. So it depends on the magnitude of k only. This is given by a rather messy expression, which I'm going to try to write down, which is delta IL, delta Jm, minus 2 k hat I, k hat m, delta JL. Sorry, this is a J, so delta IL. And then plus a half Ki, Kj, Kl, Km. Again, all unit vectors, so a hat on top. So K hat, of course, is K divided by the magnitude of K, which is, of course, omega, right? Remember, again, we have C equal to 1, right? So these are all unit vectors and components of that. So minus 1/2, a term that has Kronecker deltas only, delta Ij, delta Lm, plus 1/2, delta Ij, Kl, Km, unit vector again, and then plus a half delta Lm, Ki, Kj, unit vectors, right? So rather messy. And so it can be viewed as some sort of projection operator, and it is a remnant of the fact that these waves are transverse traceless waves, and therefore you have to have this thing appearing, right? And so that goes in there, right? And so there is this complicated dependence on the components of K. Now, in a moment, actually what we are going to do is integrate this power of over all solid angles, and then this expression here will be integrated over all directions, and that will simplify things quite a bit, right? But at this stage, this is what one has. So the dependence on the magnitude of K is through these two terms, because they depend explicitly on omega, but this depends on K hat only, right? So it only depends on the direction, but not the magnitude, right? So now we're ready to apply it to a system. Well, no, not yet, because this is far too messy, right? And in particular, what is going to be rather complicated is evaluating these Tij of k and omega, because they're Fourier transforms of the original T mu nu, right? And so the next step is the dipole approximation. Well, not the dipole approximation, because we're not dealing with electromagnetism, so it's going to be the analog of that, right? It's the analog of that. So quadrupole, approximation, right? And but it is the analog of the dipole approximation in electrodynamics. So remember how that works, right? We do that in electrodynamics and in quantum mechanics, right? So the essence of the idea, right, that is behind it is that we want to reduce that expression, which I think, in my opinion and your opinion, probably is rather messy, to something that is a little bit more tractable, where you can just evaluate some sort of integral over the original distribution of matter and energy and momentum, right? And so the idea is that this thing has a linear size, which is r. And what we do in atomic physics, this is, of course, the size of the atom. And we look at wavelengths, which are significantly larger than the size of the atom. So we look at waves that looks like that, right? So where you have a wavelength, right, lambda, which is substantially larger than r, right? So that means that basically we have omega times r, which is much less than 1, right? And so we're going to do this approximation. Now, there might be, of course, instances where this is perhaps not quite true and not quite correct, but nevertheless, at least if we do this approximation, then the results are going to be quite more tractable in a number of cases, so when the wavelength is long enough. So that means that k dot x prime, remember that what appears here, all right, this is a Fourier transform, This is essentially the Fourier transform of the Tij of x and t, right? It's a double Fourier transform in both the x, which involves the k, and in t, which gives the omega, right? The Fourier transform always involves an integral times e to the minus ikx, or e to the minus I omega t. So the integral is over the x prime, and so what appears is, of course, this factor, right? Do you remember? So in this case, what we do have is that the x prime, right, is related to the size of the source, right? Because we have an integral in dx prime. We have this integral in dx prime, right? So the integral is going to be over the region where the source term is non-vanishing. So that goes in here, and the k is, of course, 2 pi over lambda. So that's the thing that we are saying is much larger than r, right? And so that means that this e to the minus I, like that, can be approximated to first order by 1. So it's 1 I, of course, minus I k dot x prime plus dot dot dot, and so we're just going to drop that. Just use the 1, okay? Just use the 1. So let's see how that works out for one of those integrals, right? So for example, if we look at the Tij of k and omega, right? So this is given by the integral in d3x prime, right, of e to the minus I k dot x prime, right? And then, well, it's the standard definition of Fourier transform. So what appears on this side is just the Tij of x prime, and then, of course, omega stays the way it is, right? Make some space here, right? And so this factor is just taken to be equal to 1, right? And so that's all there is to it. So this is equal. Well, when this factor is equal to 1, then we're dealing with a Fourier transform of the Tij of x evaluated at k equal to 0, obviously, right? So this is equal to Tij at k equal to 0, comma omega. Right, and so, well, this is not an exact equality, so let's write it like that. Now, the other thing that is a bit of a pain at this stage is that we're dealing with all these components of the Tij, right? So I and j run over 1, 2, 3, and then we have to have the same thing here, and then we have this projection operator. But nevertheless, we know that the components of the energy momentum tensor are related to each other. They're related, of course, by the fact that this is a conserved quantity, right? It's a conserved quantity, so we have that di dj Tij, right, in real space, that this is related to the time derivatives of this, right? So this is equal to minus omega squared times the t naught naught, right? And we're talking about the parts that depend on x, where it's already Fourier transform with respect to t. So this is true, right? But, okay. So we can actually use this relationship, so we can multiply this by x alpha and x beta, and then we integrate it, and we can rewrite everything in terms of just a t naught naught through a little bit of manipulations that I'll leave as an exercise for you to do if you're interested. So we can relate everything to the t naught naught using this conservation law. So that, of course, again, cuts down on the complexity significantly. So Tij of k and omega, because of this conservation law, can be related to the t naught naught as minus omega squared over 2 times. So this expression, of course, appears in real space. So now we have to integrate that over x once we multiply by x alpha and x beta, say. And so that gives us minus omega squared over 2 times, well, not just a t naught naught, right? Not just a t naught naught, because we need to manipulate this a little bit further. And so it's going to be dij of omega, where dij of omega is some integral in d3x. And we're going to have xi and xj, which is coming from the fact that we have to multiply this by x alpha and x beta to get something useful out of it, and times the original distribution, in this case the t naught naught of x and omega. All right, so that's again a major achievement. So by using the fact that the energy momentum tensor obeys that conservation law, we can get rid of the Tij's and write everything in terms of T naught naught, right? So that is, of course, where the quadrupole moment comes in, right? Because the quadrupole moment is precisely the kind of object that will involve some integral over distribution of xi and xj. Now remember that, as we'll see in a moment, the T naught naught is going to become a rho of x. Will become just a distribution, which in general, of course, will be time dependent as well. I think I should put that in, right? And then it will be Fourier transform, so it will become a rho of x and omega. So the major achievement in this, doing this sort of, well, what in electromagnetism is the dipole approximation, and here is a similar approximation, is to bring in the quadrupole moment of the mass distribution, right? And so when you do that, then the formula for the power radiated per unit solid angle simplifies a little bit, right? Simplifies a little bit, because we only have now the T naught naught appearing in it. So let me write that again. So power radiated, right, is dP by d omega, right? Well, it has pretty much the same factors we had before. So it has the g times the omega squared divided by pi times an extra factor which is coming from using this conservation law. So the factor is there for each t, so this gets squared because there's two t's. So it's omega squared divided by 2 and then squared again. So the whole thing now is going to behave like omega to the 6th, right? And then instead of having the t's or the Tij's, we can replace those by this relationship with the Dij, which is this quadrupole moment. So let's write that out here. So it's d star, right, Ij of omega times dLm of omega. And we're still stuck with that lambda matrix, right, which had some horrendous form. And so we just write that in here again. So it's a lambda ij comma lm. And again, let's remind ourselves that it only depends on the magnitude, on the direction of the k vector, but not on the magnitude, right? Just on the unit vector built out of the k, right? And so let's put a box around us, right? Because this is kind of an important intermediate step, right? Is to be able to actually write down the power radiated per unit solid angle in terms of something that presumably we can calculate without too much work, right? In spite of the fact that the formula is complicated, we presumably will know what the T naught naught looks like for some mass distribution, right? The T naught naught is essentially the mass density. That mass density is going to change around a little bit. The object will fluctuate in size and shape. And so it's a matter of doing a Fourier transform, both in the time t, right? And then doing this integral, which evaluates the quadrupole moment of that. And then you square it, right? And you put it in here and multiply it by that other mess, and you find how the power radiated depends on the angle. And so the only assumption that comes in at this point, well, there's two assumptions that come in, right? Let's repeat them again. The first assumption is that you're looking at the far field, right? You're looking at distances which is far away from the source, which allows you to expand the exponential. And the second assumption is that you are looking at least some sort of long wavelength limit where you can use this higher pole quadrupole approximation, right? That's the only thing that came in. And so if you're aware of that, then that's the approximation that went into this formula. And nevertheless, this formula is actually quite useful. And so what's next? What's next is, well, maybe I don't really care. Maybe I don't really care about how this radiation is going to depend on these angles, right? How much comes out in what direction, right? So I'm going to integrate now over all angles. I want to know how many megawatts this thing emits in whatever direction. So I'm going to integrate over all angles, right? So that means that we are going to take dp by d omega, right, and integrate it in d omega over a solid angle, and this will be our total power, right? Integrate that. Now, whenever we say integrate over all angles with something that depends on angles, especially with a formula like that, it brings out images of headaches, right? Because we think that now we have to do this integration over angles with all these different things, and it looks like a pain. But no, it is actually easy. It is actually easy because what appears in this formula, right, is this lambda matrix. Right, this lambda matrix that depends on k, which we wrote out explicitly. And that lambda matrix contains things like ki and kj, right, with a hat on top because they're unit vectors, right, and something like that. And so now we integrate this over a solid angle, and that again is something that we do often in the electromagnetism class, and certainly the people that are in my quantum mechanics class have seen this a few times, right? And you find out that when you do an integral over angles like this, then the only chance that this thing is non-zero, of course, is when I is equal to j. And when I is equal to j, you get the average over the kx squared component and ky squared component. So that's 1/3 of the sum of the three. So this is just equal to 1/3, right, times 4 pi times delta ij by spherical symmetry. That's spherical symmetry. Spherical symmetry, right? And so you can repeat the same exercise. So this is integral for pi over the whole solid angle. You can repeat this exercise when you have 4 of these things, right, for the case. So you have a ki, kj, kl, and km, right? Again, this thing is going to be 0 unless some of these indices coincide, right? So that you get something like the first line, right? You get k squared in some combination, and so the possible combinations, well, there's only 3 of them, and then you have to figure out also the overall factor. It's 4 pi over 15. So the various possibilities are that I is equal to j and L is equal to m, or I is equal to L and j equal to m, or finally the third remaining combination. So there's 3 conical deltas. So this is delta ij, delta Lm, right, plus delta IL, delta IL, delta Jm, right? And then the remaining part, which is delta Im, delta JL, close parenthesis. Okay, so there's only 3 possibilities. All right, wonderful, which means that now you see all the agony in doing this integral has to do with the integral over lambda, because this part here, of course, does not depend on, it just depends on omega, right? So it doesn't depend on the direction. So now we have to look up what this lambda looked like and apply this rule to all 7 terms, or however many there were in that expression, right? Right, so you do that, and so you find that the integral in d omega over 4 pi of lambda ij comma Lm of k hat is equal to 2 pi over 15, which is the factor we have there. And now we have 11 times delta IL delta Jm minus 4 delta ij delta Lm plus delta Im delta JL. Okay, so that's all there is to it, to the angular integral of this guy here. Okay, and so that means that the indices I and j and Lm, well, they are going to be combined because of this, these Kronecker deltas, right? And so now you sit down and look again patiently of what the combination looks like, which gives us the P total, right? And so that is, well, we're going to get some factors of 5 because of that 15 there. So 2g times omega to the 6th, again, remember that was clear that was there, divided by 5. And now, so what's left over, the lambda is gone, and there's just going to be some contraction of these indices, and the contractions are precisely what you would expect from some sort of quadrupole radiation. So it's d star ij d of omega. So let me write that this depends on the frequency, and then dij again, right, of omega. So now there's just those two contractions, right? So the only possibility you can have is that the first two indices are contracted, the second two indices are contracted, or of course you can have this index equal to that, and that index is equal to that, and that's the next term. So that gives minus a third, and then you have the dii, right, of omega, and then that squared, and then close parenthesis. Now that, of course, is a lot simpler. That is a lot simpler. So when you look at the total power, it is immensely simpler than looking at the power as a function of the angle. And what do you need to know? Well, you just need to know the quadrupole moment, right? Remember, the dij is the integral over x of xi xj times the t naught naught. So you need to know that, and you're done. So this is actually a very useful formula, and is something that you can easily work out. In fact, in many of these processes, you don't even want to have an exact number. If you have an order of magnitude estimate, then you're quite happy, right? So that is one of the fundamental formulas having to do with gravitational radiation, and a lot of the pain and agony that we went through had to do with the fact that this wave is spin 2, that we are dealing with transverse traceless modes, and so you have to have all these projection operators flying around, which have lots of indices. And so clearly the nature of the wave is quite a bit more complicated than a scalar wave, right, like you would have for sound. But in the end, the result is nice and simple and easy and nice to look at, right? So, well, we have just a few minutes, right? So as an application, we can consider a body, right, that is rotating with some angular velocity about this axis, right, and which has certain moments of inertia, right, which are I11 all the way to I33. And we can calculate actually the amount of gravitational radiation that is given out by this body using the fact that the t naught naught of x and t in this case just becomes the rho of x and t. Right? Now we have to distinguish between two frames, a frame that is rotating with the body and another frame that is the lab frame, right? So we have a frame x here, and we have a rotating frame, which is x prime, and we have to relate one to the other, and we don't have a whole lot of time, so I'm not going to go through the details. And, but you can make certain assumptions about the moments of inertia having a particularly simple form, so that the body only, has some deviation from being spherical only in certain directions. The first thing you do find, though, is that if the body has circular symmetry about this axis, then there is no gravitational radiation. So if you have a spherical, the body has to have some odd shape so that you can give off some gravitational radiation. And so that, of course, has far implications because, for example, if you have spherically symmetric collapse, also you don't, for a star, you don't get any sort of gravitational radiation. So in this case, you find that the power, first of all, gets radiated at a frequency which is twice the base frequency at which this object is rotating. And the formula is 32 times g divided by 5 c to the fifth. So we put the speed of light back in because we express everything in CGS units, right? So in terms of centimeters and so forth. And it is proportional to the sixth power of the frequency at which this body is rotating. And it is proportional to this moment of inertia squared times e squared. So what is the I? Well, the I is equal to I11 plus I22, which in this case, I think every other moment of inertia is assumed to vanish. And so the sum of the two appears in here, and the E is the difference, right? So the difference, this E, is equal to I11 minus I22, and then divided by I itself. And so if you have an idea of what the moments of inertia are for this rotating body, then you can estimate the amount of total gravitational radiation that is emitted. It will grow very rapidly as a function of the frequency. But of course, usually for astrophysical objects, this frequency is not that high, right? So you don't have really much of a chance of enhancing the signal by going to high frequency. Instead, what you should look for objects that where these moments of inertia are kind of unbalanced. And so as an example, I think is you can look at, well, of course, the simplest case is would be a mass here that is going around like that, right? And so, for example, you can achieve a non-vanishing quadrupole moment by just looking at Jupiter and its orbit. Right? Jupiter and its orbit. So in this case, the moment of inertia is just related. So if you have an object like this, then the power, the total power, is going to be proportional to the mass squared times the radius to the fourth power, right? So the moments of inertia are traded for the mass and the distance. And you can look at, given the orbit parameters for Jupiter, what the distance from the sun is and what the mass is, you can estimate how much gravitational radiation that thing is going to radiate off. And it is not a whole lot, okay? It's 5.3 kilowatts. Right, 5.3 kilowatts, not a whole lot of radiation. So no chance of detecting something like this. The other possibility is that you look at a binary pulsar. So the other possibility is that you look at a single pulsar or a binary pulsar. Right? And well, both of them will emit gravitational radiation provided the parameters are right, that you have some non-vanishing moments of inertia according to that formula. But of course, the binary pulsar one is the one that works extremely well. And again, that is how gravitational radiation, in fact, was detected in the first place, right? Because the answer was, the question was asked, of course, a long time ago, whether gravitational waves actually do exist. And of course, the best method to determine whether gravitational waves exist is by direct detection. So you build some huge detector, and then you wait for some wave to come in, and you look at some effects of those shear waves. And that has not happened yet, right? But what has happened is that if you take a binary pulsar, right, which is two neutron stars, right, where one is orbiting around the other like this, right, and typically they are, masses which are of order 1.4 times the mass of the sun, then you can calculate the amount of gravitational radiation that is emitted according to this formula, right? You just calculate the total, say, for example, right? And you need to know the orbit parameters very well, right? But that you can do, right? You can, in fact, even calculate the general relativistic precession of the perihelion, so you know the eccentricity, you know everything, the major semi-axis and so forth. And this thing will radiate because, in fact, for a typical binary pulsar, the time that it takes for one to go around the other is just 8 hours. So they go around pretty quickly. And the eccentricity of those orbits in some cases is significant. And so the orbital parameters are just right so that this thing emits a significant amount of gravitational radiation. It's significant enough for it to be detected. No, we can't detect it because it's too weak, right? We can't see it on Earth. But what we do see is that the orbital periods are changing, right? Because the orbital periods are getting longer because this thing is slowing down due to the fact that it does emit significant amount of gravitational radiation. So the energy that is in the orbital motion is decreasing. And it was Holze and Taylor who back in 1972 at Princeton started to look with a magnifying glass at some of these pulsars, right? And they found some where the decrease in the orbital period, right, the changes in the orbital parameters were in exact agreement with general relativity, which predicted by how much the orbital motion would slow down due to the emission of gravitational radiation, because this formula tells you, right, the formulas were out on the blackboard, and the quadrupole approximation works pretty well, right, would tell you precisely how much would be radiated away. And so they made a plot in the change in the orbital parameters, right, with the data they had, because they could follow this orbital motion and see how much it slowed down. And then on top of that plot, they plotted the curve that corresponded to the expected slowing down due to the gravitational wave emission. And of course, the two are right on top of each other. So the summary of this is that nowadays we have not detected gravitational waves in the lab, right, because they happen to be rather weak, and the detection apparatus is extremely sophisticated and complex and requires huge baseline interferometry. But nevertheless, their existence has been verified indirectly, because we can see that the slowing down of orbital periods is precisely in agreement with general relativity if you use the formulas we discussed today for the emission of gravitational radiation. And of course, they got the Nobel Prize for this, right? They got the Nobel Prize because they followed these pulsars for a few years, but then, by now, I think from 1973, we have like 30 years of records, not for just the original one, but several others. So you can check that these things just work out beautifully, that the whole theory just agrees very well with what is observed. So here is a picture of Joe Weber. So this is one of the original bar detectors, right? I won't have time to go into that. So here is one of these aluminum bars that he built at the University of Maryland. Now, Joe Weber was the husband of Virginia Trimble, right? And he was on the faculty here for a long time until he passed away about 10 years ago. So he is the person that really developed this whole theory of gravitational wave detection. He was a pioneer in his field, and he built this big bar detector and eventually detected nothing, but nevertheless he developed a lot of the theory and the technology to look for these kind of things. And these bar detectors, I mean, I'm not an expert, but I think they're a little bit passé by now. I think there's better ways of going about trying to detect gravitational waves. These things are intrinsically noisy. They just suffer from all sorts of thermal noise and vibration in the floor, and anybody, a grad student, walks upstairs, you detect a signal, and so it's not a good way to go about. So the best way to do it today is, of course, by putting some huge masses, massive order of tons, miles away from each other, and then measure the distance. Measure the distance, which you can do with lasers, right? We put mirrors on these things, and you can measure the distances to, well, almost fractions of an atom, right? An atom size, we're talking about, 10 to the minus 8, 10 to the minus 9 centimeters. So typically, these gravitational wave interferometers can measure fractional displacements, which are of the order of 10 to the minus 20, 10 to the minus 21. And so they built those. The arms of the interferometer are a few miles long, 1 mile maybe. So they're huge and they're very sophisticated, and of course then the hope is that what you will do at some point is build more than one, because if you have more than one, then you can do coincidence experiments. Because if a wave is coming in from a binary pulsar or whatever it is, or some catastrophic black hole coalescence, then if you have several detectors, the signal, of course, travels at the speed of light. You're going to detect it at different locations at different times. So that means that if you have a detector like LIGO in Louisiana or Washington, have another detector, Virgo, in Pisa or in France somewhere, then they will detect the signal at about the same time, but not quite. So you'll be able to reconstruct where the signal is coming from, and that's so that's kind of the future. And so anyhow, we're out of time, and so any questions or comments? Yes?
How can you detect it with light if light itself is affected by the gravitational wave, unless it's very short wavelength?
Light is affected by gravitational waves, yes. No, but you need huge masses. You need something that has very significant gravitational interactions, right? And so you want to have a lot of atoms, something that weight is crucial, right? Weight is crucial in determining gravitational effects. So you suspend masses which are made out of, I don't know what they're made of, lead or steel or something, which weigh several tons, and they're suspended by wires from the ceiling. And they just sit there. Normally they sit there, they don't do nothing, but if there is a gravitational wave coming in, it will distort space-time, so those masses all of a sudden will start to swing, right?
Yeah, but the light itself that you're using to measure the distance between them will go through
the light will be
distortion.
the light will be affected as well. So you have to take all those effects into account. But remember, gravity acts very differently on light than it acts on the masses,
Okay,
right? So you can
you're
sort.
counting those on.
Yes, so you're sorting all of that out. Yes. Yeah. Any more questions? All right. I'll see you then next Thursday.